the binomial to normal approximation. In this binomial distribution, we flip a fair coin 80 times. The probability of getting heads is 0.5. The coin was flipped exactly 80 times, and the discrete random variable x represents the number of heads that you get. So out of 80 trials you could have 0 heads, or you could have 80 out of 80 heads, and any value in between. And if we were to graphically have a look at the probability distribution, it looks like this. So we've got probability against the number of heads out of 80 flips of the coin, and we can see that the distribution is actually symmetrical, and it looks very similar to a normal distribution. Here is another example for binomial distribution, and once again we have a large number of trials, and this probability is close to a half. So we see symmetry again. It looks like a normal distribution. And another example where again we can see the individual discrete probabilities, because the binomial distribution is discrete, large number of trials, the probability of success is close to a half. We have the shape of a normal distribution. In this binomial distribution, n is still large, but p is nowhere near a half. This time our distribution starts here. There's nothing on this side. We're looking at the number of successes out of 80 trials along this axis. So this actually goes up to 80, but there's nothing to show on the graph beyond like 8, 9, 10, so the rest of the graph is missing there. So we have a distribution that has this shape, and clearly this is not symmetrical. This shape looks nothing like a normal distribution. You can find this in the Edexcel formula book. For the binomial distribution, we have a formula for the mean, n times p. You just multiply these values, and a formula for the variance, n times p times 1 minus p. Now the formula for the variance, you might find this in other sources written as n p q, where the q represents 1 minus p. If p is the probability of success, so this is success, just the p, then 1 minus p is the probability of failure, which is represented by q. In this binomial distribution, we have a large value for n, and p is 0.5, and we can see the shape of the distribution resembles a normal distribution. The mean is n times p, so this will give us the mean of the distribution. And 300 times a half is 150. And the variance, n times p times 1 minus p, which is 75. So now I'm going to attempt to do a normal distribution curve with these parameters, with this mean and this variance, on the same graph. And this is what we get. So the mean went here in the normal distribution, and the variance went here. And it's good practice to use a different letter for your random variable when you go from the binomial distribution to the normal distribution. And then removing the underlying binomial distribution, we can use just the normal distribution to calculate approximate probabilities that we would find difficult to calculate in the binomial distribution, but we can just go ahead with the normal distribution instead. So here is a quick summary of what we've done so far. So binomial distribution, the larger the value of n, the better the approximation will be, and p has to be close to 0.5, and these conditions will lead to symmetry in the binomial distribution. And you've seen from the graphs, we can use the normal distribution as an approximation for calculating probability. And n times p was the mean, that goes there. N times p times 1 minus p is the variance, which goes here. So in this example, we know that the binomial distribution is discrete and the normal distribution is continuous. This random variable y can take any value, but the discrete distribution here can only take values for x between 0 up to and including 300. So let's say if we were doing a question like this, the probability we have exactly 140 successes. Here's the binomial formula, this one here. So if I try and just do this part in my calculator, so 300 C 140, I'll get a math error. The number's too big for the calculator to handle. So in the past, when this calculator, the Casio ClassWiz, and various computers were not available, this would cause a serious problem. So the workaround was to use the normal distribution. This probability can be worked out using the calculator. So it's equals 140, so it's the binomial probability distribution, option 4. Option 2, x is 140, n is 300, p is 0.5, and here's the answer. But what you'll find is a question like this in an exam would be worded as, using a suitable approximation, calculate the probability. And if you're using the method that I've just shown on the calculator, that's using the exact binomial distribution. It's not using the normal approximation. So this answer would score you 0 marks. You would have to use a normal approximation. If the question mentions you have to use a suitable approximation. Now if we go to the normal distribution and calculate the probability that we have y equals, now we already know that equals in the normal distribution, or any continuous probability distribution, will just give a probability of 0 because you're not shading anything. Now the workaround is called a continuity correction, which is always applied when we start with a discrete distribution and we use an approximation to the discrete distribution, like we're doing here, using the normal distribution to approximate probabilities from the binomial. So in reality this is not what we would calculate. What we would calculate would be the probability that y is between 139.5 to 140.5, and that would give an area that you would shade on a sketch. In this one, for equals, we're not shading anything. But in this one there would be a region between 139.5 and 140.5 that we would shade. And a reason for using these two values, if you were to round values in this interval, they all round to 140. More on this in the next video.